Hello everyone, in this video I will talk about how to solve AP Physics C, Electricity and Magnetism free response question number 1. So first let's look at the setup. Students perform an experiment to determine the value of vacuum permittivity epsilon naught. Sphere 1 is non-conducting. So we'll see that non-conducting is an important condition for this question because we'll see the conducting case where the charge will redistribute. So for non-conducting sphere, the charge will be distributed uniformly on the sphere. And also the same thing happens for sphere 2. Okay, so sphere 1 has charge positive Q and is attached to an insulating rod. Sphere 2 is non-conducting with charge plus Q, capital Q, and has mass capital M. Sphere 2 is hung from a string of negligible mass and length L. Sphere 1 is brought near without touching. Sphere 2, as shown, equilibrium is attached when the centers of the two spheres have the same vertical position. So if you look at the picture, the center of sphere 1 and center of sphere 2, they're at the same level. Okay, so that guarantees that the force between the two spheres is along the horizontal direction. So in this case, the sphere 1 will apply a repulsion on sphere 2 to the right. Okay, so we can use that for the free body diagram. And the distance between the two centers is d, okay, and the string is at an angle theta from the vertical, so that's the angle theta. Now question A, on the following dot that represents sphere 2 at the position shown in the previous figure, draw and label the forces that act on sphere 2. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Okay, so this question is about the free body diagram. So let's look at the free body diagram for sphere 2. So here's question A. Now let me draw a similar dot to represent sphere 2. Now because there's a string attached to it, so there must be a tension force T. Okay, so here's not very straight. Let me draw this. Now the repulsion force is horizontal. So that's from the little charge Q, little q, and it's to the right. Now the gravity is in the vertical direction, so I'm going to draw this mg here in a vertical direction. Okay, and that's the free body diagram. Now question B, derive the relationship between distance d and the angle theta to show that d equals this square root of qq over 4 pi epsilon naught mg cosine theta. Okay. So we'll see that we're going to use this equation here to plot a relation between d squared and 1 over tangent theta in a later question. So we need to derive this equation right now. Okay, so let me put some angles on the diagram. So here is angle theta. Okay, and the whole system is at equilibrium. So if we build a coordinate system such as the horizontal direction is the x-axis, okay, now the vertical direction is the y-axis. Then we can write down the equilibrium condition for both directions. The net force sigma fx, okay, represent the net force in the x direction is given by there are two forces along this direction. Fq is positive to the right, so in the same direction as positive x. Now in the left direction, there's a tension force component. So let me decompose tension force using the angle theta. So it's T sine theta, because this direction, this side is the opposite of the angle theta. So that's angle theta. So it's T sine. That's why this term is minus T sine theta. Okay, and that's all for this direction equals 0. And the reason it has a negative sign here is because T sine theta is to the left, which is negative direction. Now in the y direction, we have a similar equilibrium condition. So let's write down net force equals 0. And in this direction, now let's decompose the tension force into this direction. So that's T cosine theta. Okay, and that is positive direction. So positive T cosine theta. The gravity is negative mg equals 0. All right, so now with that, we can solve for Fq, because we need the force between them. Right, so let me write it here. Fq is 1 over 4 pi epsilon naught Qq over d squared. That's Coulomb's law, right? The force between them is given by the Coulomb constant 1 over 4 pi epsilon naught and the two charges product, and divided by the distance between them squared. So we need to solve for this one, right? Fq. And to do that, I want to use, let me label this equation. Let me use equation 2 first. So from equation 2, I can solve for T, which is mg over cosine theta. Now substitute into equation 1. Fq equals T sine theta is then given by mg over cosine theta times sine theta. So that's mg tangent theta. Okay, so let me substitute in equation 3. Okay, so equation 3 substitute into here. We have 1 over 4 pi epsilon naught Qq cosine theta. D squared. Equals mg tangent theta. So now from there, I can get d squared equals Qq over 4 pi epsilon naught mg tangent theta. Right, so we can have that, right? So now let's take the square root. So d equals square root of this whole expression here. And that's exactly what we need here for question B. All right, so let's look at question C. These values are collected in one trial. So we set the two charges, and then the angle now is 12 degrees. And we also know the measure the distance between the two spheres is 0.057 meters. Now calculate the expected force of tension exerted on sphere 2 by the string. So now this question is not about the D here or the angle theta here. They're both given, right? Both given. So this question is about this question is more about the yeah, sorry about that. Sometimes when I swipe, it's not moving direction, it's actually magnification. Sorry about that. Okay, so here is D. So this question is not about the D or theta. It's actually about the tension force. So remember, tension force is mg over cosine. So for question C, so the question is about tension force equals mg over cosine. But we don't actually know the mass m, right? We don't actually know this m here. So we need to use the question B's result here to get mg expression in terms of d, theta, and qq, and then we can plug in here. Okay, so let's first get the mg from this equation. So mg equals, we're going to square the equation here, so we get qq over 4 pi epsilon naught, and then divided by d squared. And that's also a tangent theta. Okay, so now let's plug in this expression here. Then we get qq 4 pi epsilon naught d squared, and then tangent theta, and then cosine theta. So cosine theta is from this expression. And we know tangent theta is sine over cosine, so cosine will cancel out. And then we get qq 4 pi epsilon naught d squared sine theta. Okay, so now we can plug in the numbers. Both QQ are 6.0 times 10 to the negative 8 coulomb, so we're going to square that. And 4 pi epsilon naught, 1 over 4 pi epsilon naught is actually the Coulomb constant. So that's Coulomb constant is 1 over 4 pi epsilon naught, which is 9.0, 10 to the 9th. Then that should be SI unit Newton per meter square over per Coulomb square. So that's the SI unit for Coulomb constant K. So I'm going to substitute in this number directly. Okay, so it's 9.0, 10 to the 9th. That represents the 1 over 4 pi epsilon naught. Now, how about D here? D is 0.057. We need to square that. And then sine 12 degrees. That's 12 degrees here. Okay? So I already did this calculation, so let me check this number. The number here is 0.048 newtons. Okay? That's question C. Question D. Now the student do the experiment and then vary D here and measure the angle theta after equilibrium is reached. The students use the collected data to plot the following graph: d squared versus 1 over tangent theta, and they got this line, this scatter point. Okay, so this should satisfy a straight line relation. So we need to draw the best fit line for this data. And then we'll use that line to estimate the vacuum permittivity. So first, let's figure out why we have a straight line here. So let's look back at the question B, where we have the relation between D and theta. And question C, question D. So if I square the two sides, I will get D squared equals QQ over 4 pi epsilon naught mg, and then there's a 1 over tangent theta. So I want to single out this 1 over tangent theta because the experimental data is collected, they are collected against 1 over tangent theta. So I want to use this as the x-axis and d squared as the y-axis. So now we see there's a relation, there's a constant here which represents the slope. Let me put a circle around this term, that's the slope. So let me call this S. I usually call slope K. However, we already have K here for the Coulomb constant. So I want to call this one S here, that represents slope. Then we can rewrite this equation as d squared equals S times 1 over tangent theta. And the slope S will be from the best fit its slope. Okay, so now think about how to do the fit here. So that is like a must-have question for every AP physics exam. So you need to fit the experimental data. And here I'm going to just draw a schematic equation, schematic picture here for the fitting. So you should have a straight line going through all these points, okay? And these are the scattered points. So you want to have a straight line going through as many points as possible, and then the remaining points will be uniformly distributed along the two sides of the line. So you should have something like that. Okay, so here just schematic. You should use your ruler to draw a straight line through all these points. Okay, and then you would identify two points along the straight line, the best fit, and then you will do the second part of the question. You will estimate the slope. Okay, so you're going to pick like 2 points here and there, and then you will get their coordinates. That's 1 over tangent theta 1 over tangent theta 2. So that's the x coordinate, and we should have d2 squared and then d1 squared. Okay, and then the slope is given by S is given by d1 squared minus d2 squared over 1 over tangent theta 1 minus 1 over tangent theta 2. Okay, with this set of data, you'll be able to calculate this slope S. Okay, we'll get some data there. Now suppose that you already did that calculation, and let me show you one of the calculation I did. The numbers we have here is, for this number we have 10.5, 0.0075, and this point here has coordinate 4.5, 0.003, and then you are plugging this set of number. The calculation is given by this equation, and then the answer is 0.00075. Okay, that's the slope, and slope equals this expression. We already talked about that. So the vacuum permittivity epsilon naught is given by QQ over 4 pi. Now it's S, the number we got from the best fit, or mg, sorry. Now let's plug in the numbers. QQ is still 6.0 10 to the negative 8 squared. And then 4 pi. Now the number here is 0.00075. That's for S, the slope. And the gravity here, the mass here is 0.005. And 9.8. Okay, and the number I got from these calculation is 7.8 times 10 to the negative 12. The unit here is coulomb per Newton square meter. Okay, so that is very close to the exact number, 8.85. I would say it's very close because this one is a really rough data estimation, and the experimental setup is also very rough. It's not very accurate. So that's why we have some deviation from the correct number. Okay, sorry about that. Okay, so now let's go to the next question, this one, E. The students modify the experiment by replacing sphere 1 with a conducting sphere 3 that has the same size and charge positive Q. The experiment is repeated. The circle in the following figure represents sphere 3 when sphere 2 and 3 are at equilibrium. On the circle, draw a single positive sign to represent the location of highest concentration of the excess positive charges. That's 3. And it's conducting. Okay, and you also want to talk about why you do such a drawing. So remember that the sphere 2 here is positive, and sphere 3 is also positive, carries positive charges. So they will have repulsion between them, right? And the now it's conducting, so the electrons on sphere 3 can move to the right side because they're attracted by the sphere 2. So, and also because of that, the charge movement, electron move to the right, the left side becomes positive charged. So that's why we should draw, for question E, we should draw such a picture where we have negative charge concentration, right, on the right side, and the left side will have positive charge. So we, because the total sphere, the whole sphere here is to carry positive charge, so we should have more positive charge than the negative charge in the diagram. So draw something like this. However, the question only requires a single positive sign, so you should get rid of all these extra signs, positive signs, and also this negative sign. Okay, leaving only just one positive sign here. And my drawing here is meant to show you the redistribution of charges, and the right side could be negative, okay, due to the attractions between electrons on sphere 3 and the positive charge on sphere 2. Now part 3. In the original experiment, when the centers of two spheres are a horizontal distance d1 apart, the string makes an angle theta 1 from the vertical. In a modified experiment, when the centers of the two spheres are at a horizontal distance d1 apart, the string makes an angle theta 2 from the vertical. So that means that we need to keep the same distance for the two spheres and study the angle difference. Okay, so is theta 2 greater than, less than, or equal to theta 1? Now, since we already know the charge distribution is like this, right? So let me also draw the sphere 2. So the force between the two spheres, the repulsion between them, now will be smaller. So this F in the case E here will be smaller than the previous FQ that we drew earlier. Because of this redistribution, so the positive charge are further away from the sphere 2 and negative charge is closer to sphere 2, right? So that will make this repulsion smaller, and that means a smaller angle. So theta 2 is less than theta 1. All right, so that's the question number 1.